You know, the little tomato seeds you and Nancy planted in your garden, how they grow into nice red tomatoes.
For the third time, the observers have come together for this one purpose: to learn, to engage, to understand and observe the frontier. For those who have been here before, welcome back. And for those joining us for the first time, we hope to inform, and we hope you have fun.
Well, it's like this,
Researchers spend an unfathomable amount of time either trying to get credit for their work or keep somebody from stealing it. I will consider this a major failure if anybody in here does not steal this and go start predicting earthquakes. We first have to begin with what I call the solar system circuit, what it is and what it isn't, and we're going to go over two little rules that we use just to sort of get us all on the same page to get started. Now, what this is and what this isn't. This is not actionable information. We do not yet have the ability to forecast seismicity in a way that governments can commit resources, the way that people need to be notified in such that it could create panic, something like that. It's nowhere near hurricane forecasting. But what it is a method for narrowing down the seemingly global risk for earthquakes at any given time to about 10, 15, to 20% of the Earth's faults, updated every few hours to every day. And those capture 70 to 80% of the magnitude 6 and higher earthquakes. So this is informational rather than actionable. But could you imagine if we tried to go from knowing nothing about when a hurricane was going to come to what we have today? There are intermediate steps. It's a progression over time, and I think this is going to be an intermediate step, and that's what we're going to be presenting here today and tomorrow. The most recent rule, it's the second line you have there. What the most recent rule is it states that the very last alert map, or the very last alert that was posted before such a big earthquake, must count. It doesn't matter what was on alert in the post before. If an area had been on alert for 10, 20, 30 straight maps, the moment it comes off of a map, it goes off of alert. And so this creates a very, very simple and ultimately restrictive view of success. When a big earthquake comes, what was the very most recent earthquake map, risk map that was posted, and is the earthquake in question included in the alert zones, or is it not? We also have the highest alert rule. Those who know about our earthquake alert maps know we have red lines, there are alert stars, there are yellow lines. We've come to notify things with blue and green as well. Well, for the model, we only count the successes, the hits of the highest possible alert that given day. It is normally an alert star or a red line, for those of you who are well aware with some of our earthquake maps. That's pretty much how it goes. We will oftentimes put a lot of different colors on there, but in terms of success versus failure in the model, it is indeed all about what is on highest alert at that time. So, these are the main sections that we're going to be going through. What we're going to be doing this morning here is talking about the results and some of the conclusions that we can make from what has actually happened over the past few months. Then a little bit later this afternoon, we're going to be talking about why some of this works, some of the factors that are used. And then tomorrow, to close the conference, we're going to be talking about how this moves forward and how we unleash the power of all of you guys. So, we're going to start, like I said, with the results and the conclusion. What has happened so far, and what does that mean? Now, before I go any further, there are 2 papers that are now published that you guys can find at quakewatch.net. That would be quakewatch.net there. They're in the top right. They're the 2017 papers, and they do go along with this presentation, and I think that after watching this, it will be much more fruitful to read those works. And so this is an example, just one example, and we're going to go through some of them just to start here. On one side, you can see the alert map that was posted most recently before the official USGS intensity field map for the 7.9 that struck Papua New Guinea on December 17th. Now, on the alert map, you can see that, we've got a yellow line, a yellow arrow, we've got some green on there, but the red alerts there are confined to about 15 to 18% of the entire world's fault system. Again, you cannot put, most of Chile and Bolivia and southern Peru on alert and then everything in northern Oceania all the way across to Papua, Indonesia. So it's not yet actionable. But narrowing down like this is a first step. Now, interestingly, that little green circle we have there over Hawaii, that's another thing we're going to talk about. This one was done a little bit more in the words in our alerts. So we posted this alert on Twitter, which is where most of the alert maps come. This again on December 16th, when that alert map was posted from the previous slide. Hawaii had basically been about average. None of the things you're reading here being, having 10 magnitude 3 and higher earthquakes in the last 30 days, none higher than 3.3. That's not exactly below average. That's about run-of-the-mill. But the factors said that they should outdo those. Now, of course, we did not expect a 6-pointer to strike in Hawaii, and so they were not meriting a red alert or something like that. But it's very interesting to see if we could get this to work on other levels. And for those who don't necessarily remember, one day later it was a 3.8. The day after that it was a 3.6. And the day after that it was a 4.5. Much higher than even we actually expected. So in the 3 consecutive days after that forecast, the factors didn't really make us wait very much. But of course, this is just an example of how this works across the magnitude scales. And this one actually didn't even have any of the subterranean signals that we've come to call Blot echoes, and which we'll talk a good bit about this weekend. This was purely based on the atmospheric signatures that we had seen in this area in the past. So this is probably one of the most well-known alert maps that we've ever posted. This was on November 11th. 2 alert stars and a little red line in the middle. Of course, you'll remember from the highest alert rule, the stars are the ones that really matter. Well, it was just one day later, of course, that the 6.1 struck Japan. Luckily, it did so fairly deep and wasn't even really felt too badly. But of course, the 7.8 that struck New Zealand and created a small tsunami, one of the largest events that country had ever seen, occurred just a day after that on November 13th. And of course, you can see that where that earthquake occurs in New Zealand is just slightly south of the alert star that was posted on November 11th, but November 12th, after the Japan event, we shifted all of the alerts down to the southern hemisphere, and you can see over in eastern Oceania, that alert really did spread out to the corners of the fault zone and was inclusive of the earthquake event. By the way, the second largest earthquake of the day that 7.8 took all the seismic news, was rated anywhere between 5.8 by the USGS and 6.2 by the Argentinians, where it hit their inland fault there. So this was kind of a bananas 48 hours, so to speak, with the Japan event, the New Zealand event, and the Argentine event, which we ended up not being able to count for the model because the USGS had it at only 5.8. Of course, many will remember the 6.6 that struck Italy back on October 30th, 2016. This was indeed the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This was the 14th largest earthquake in the history, in the recorded history of Italy. Second largest of the last century. You have to go back to 1980 to find a 6.9. So this is a really rare event, and of course this was the alert map that was posted just beforehand. We had red line alerts pretty much all over the Pacific, but via the highest alert rule, the one that really counts was the alert star. The alert star sat over Italy on October 29th, remained there the next day, and actually that little red circle in the center of the alert star is where the 6.6 struck. Of course, this would be a great example, one of a few we're going to see here, of the southern hemisphere, continuing specifically South America. They really, in Chile, Peru, Bolivia, and even parts of western Brazil that end up taking the seismic activity, they really give themselves away. As you can see in this map that was posted November 3rd, 2016, we do have a couple of blue arrows, and for those who are really keen and remembering how we do some of these alert maps, those are always following the atmospheric signals and where we expect those to go. But indeed, the only place that was actually on alert at this time was South America. And the very next day, a 6.3 struck, and that was not in the red star there, but the orange star. Another example is right here. They basically gave the exact same signals 2 weeks later. This is November 18th. And it was just a little bit north of the one that had previously struck. So far, there have been no magnitude 6 earthquakes to strike South America that have not hit a highest alert at that time. It's currently running at 100%, which certainly could not expect to last forever, but it's one of the areas that presents the merit of these pre-seismic factors as well as any other. Sometimes there is no map needed whatsoever. At 3:20 a.m., right in the middle of doing the news, the morning news actually, we posted this because we saw a couple of Blot echoes. Again, we're going to go over what those are in the Philippines and Indonesia. Throughout the rest of the day on October 18th, that activity turned out to be not so minor. We actually had 4 more Blot echoes, and we had the 6.6, and that was 1 day later. On the 19th, again, the Philippines and Indonesia being the only areas in the world on alert at that time. So, in one of the papers that you guys have there on quakewatch.net, you're going to see this chart in there. Now, the first paper you have on there, Davidson 2017, describes the first 100 days of forecasting using this model, from the middle of October 2016 until January 23rd, 2017. And so these are all 24 ranked by magnitude, magnitude 6 or larger significant earthquakes that have occurred during those first 100 days of the model. And just an FYI, we updated at 100 days. We will update again officially at 1 year and at 1,000 days. But so in the first 100 days, there were 24 of those events. Only 4 of them did not strike the alert zones. And you can see pretty interesting little distribution here. And a point of note, it would be theoretically possible if you were aiming to just put a tiny amount of the world on alert and get a disproportionately large number of earthquakes, to just put the Philippines, Indonesia, Solomon Islands, Papua New Guinea on alert, maybe places like Japan. But take a look at where these misses were. The Solomon Islands, Papua New Guinea, the Tajikistan one was interesting, and Indonesia. 3 of the 4 misses we have had during the run of this model were in the precise areas that you would expect to see the most earthquakes. As in, if you were going to just have a watch in one place and never move it, and just hope that they took more earthquakes than, the fault coverage, those are the areas you would want to pick. But so what we have is 20 out of 24 successes using 17.9% active fault coverage. 20 of 24 is about 83%. Because so many of the faults of the highest alerts were falling in the ring of fire, that 17.9% is actually not representative of the number of earthquakes that we would expect based on regional, national, and then 5, 10, and 20-year historical periods. We could expect that 17.9% of active fault coverage to capture between 25 and 35% of the magnitude 6 and larger earthquakes. And you'll see for the paper we chose to play devil's advocate and choose the highest possible number there. We chose 35%. And so we ended up expecting to get about 35% of the magnitude 6 and higher earthquakes, and in fact it was 83.3%. The expected successes based on random distribution should be between 7 and 10. 99.1% of the time, the model should get less than 14 successes. And that p-value right there, for those who don't know statistics, that is basically the chances that this is randomness or it's blind luck, or basically that the significance of what has happened here is due to error or some other ghost in the numbers, so to speak. We're going to quickly start getting into this magnetic Earth and global electric circuit issue here, because that's really where a lot of this comes in. 100 days, phenomenal statistics. Now we need to start explaining why this works and some of the things we're looking at on a daily basis to create some of these fault zones, how we shift them from a little area in this part of the world to a little area in another part of the world. And we're just going to quickly break the surface on some of this, and then we're going to quickly break before Dr. Claridge gets up here. So we're going to start here and talk about solar and geomagnetic factors, and when we come back at the end of the day today, we're going to be talking about the atmospheric and the global electric circuit signals, and then the deep earthquake mystery when we're going to be talking about Blot echoes. But let's quickly talk about the sun. So this is the Solar Dynamics Observatory viewing the sun in 211 angstroms. They have assigned the color pink to this. It really doesn't matter what color it is false color. But what this view is designed to do, it is designed to pick up particles in the corona, namely ionized iron. Now, when it picks up these particles, it tints them sort of pink, except if it picks up a lot, it'll tint them white. Now, above the sunspot regions, those who follow the show and those who know about space weather, we see the bright umbral magnetic fields. Those are bright because they're containing a lot of particles. This camera is reading a lot there. The particles are trapped in the magnetic field. But down there on the bottom, you see an opening. Those who know the show and know the sun know that is the coronal hole. The reason why you don't see anything there and why it's registering as black is because unlike those areas above sunspots where the magnetic fields are coming in and out of the surface of the sun, at a coronal hole you have the interplanetary magnetic fields, and these go all the way out past Pluto. Every planet has a magnetic connection to the sun, and they all connect back, sort of like a copper wire connecting them in space, except instead of a wire, it's a direct magnetic field connection, like a Birkeland current. And they all connect back to these coronal holes. Now, in addition to basically having the magnetic power of the sun, which again streams out past Pluto, connecting and disconnecting and sweeping past the Earth, they're also blowing out Alphen waves. They push solar wind faster than it otherwise would have gone. It drives magnetic changes in the solar wind where these ionized particles will actually flip and start approaching the Earth at a different polar angle, so to speak. This is the coronal hole that faced Earth on March 11th, 2011, the day that Japan had a 9.0. and the Fukushima tsunami occurred. This was 13 months later on April 11th, 2012, the only day two 8-pointers have ever struck the same area on the same day, an 8.6 and an 8.2 in Sumatra. This was 2013, the biggest of that year, an 8.3 in the Kamchatka Peninsula of Russia on May 24th. Powerful coronal hole there. This one was fascinating, and it's where we're going to leave it. It's where we're going to start when we come back this afternoon. This coronal hole is only presenting itself visibly in a very minor way, but can you see, especially up to one side, how there's sort of this intermediately darker area? It's not as dark as the black coronal hole areas you see, but sort of this wedge on the northern hemisphere of the sun is just slightly tinted a little bit darker. Well, that was actually a massive coronal hole that just happened to only be presenting very visibly towards the equator because of some of the sunspots you see around those coronal holes and in between them there, really sort of polluting the otherwise glorious view of that coronal hole. On that day is the day 7.8 struck very deep off the coast of Indonesia, not on the fault line, but where, in fact, the north and south magnetic poles are tracking. Those who have heard this story before know where we're going next. But for now, this is where we're going to leave it. The sun is going to be telling us when we need to be watching the most, not only with coronal holes, but those who have read our 2015 peer-reviewed works that Dr. Holloman, the statistics professor at Ohio State, and Dr. Kong Papu Yen from Goddard were kind enough to co-write with me, know that it's the solar polar magnetic fields that are really driving the magnitude 8 seismicity. And those same polar fields, the only difference between a solar polar field and an interplanetary magnetic field from a coronal hole is one comes out the pole and one comes out and directly faces Earth. So the sun is about the timing. When we come back later this afternoon, we're going to be looking at where on Earth these risks are going to be found when we see these types of factors in the atmosphere and below the ground as well. Quickly to review, using just under 18% of the world's active faults, we successfully captured or covered 83.3% of the magnitude 6 and larger earthquakes. That is way more than is expected, and it begs for an explanation. Now, we started to talk a little bit about timing when we were looking at the coronal holes, and the sun tells us really when things are going to be active. Now, before we get into how we nail down some of the locations where these earthquakes are going to occur, an important point has to be made about the changing Earth. 150, 200 years ago, presume in this hypothetical that we have all the same access to technology and data we have today. I don't imagine that the space weather factors, this solar phenomena that we see, would have been as influential over the Earth. And that's because we had a much stronger magnetic field. It might have been different in some of the ways it couples. Perhaps some of the coupling events would have been different, but just as Michael Claridge said that our magnetic field should be thought of as more than just the shield of the planet, just as much that is true. In a same vein, the magnetic field does determine how much of that solar energy comes into the atmosphere versus how much gets integrated into the magnetic field or deflected off into space. And we are down about 25% in Earth's magnetic field since just the 1800s, which means that these solar phenomena should be more influential now than they used to be. And as long as that trend of weakening magnetic field continues, these factors should become more and more robust as the sun and galactic cosmic rays basically get a free shot at the global electric circuit, at the atmosphere, and at the lithosphere. So this chart right here is one that some of you may recognize if you've seen some of our older presentations, but we're going to go through what some of these things are. Now, I mentioned before that when this earthquake, when this coronal hole faced us, we had a 7.8, very deep, not near a fault line really, but at the area where the north and south magnetic poles are set to meet. Well, that would be the white arrows that you see coming over on the right side and the right side top, right side bottom. That is the north magnetic poles tracking movement and the south magnetic poles tracking movement. Now, even though the north is still trekking across the Arctic Sea, and even though the south has already left the continent of Antarctica, it is going much slower. They are actually set to meet on the southern side of the equator, despite the fact that the southern pole is much closer to that now. And so that's what that star is right there off the coast of Indonesia. Now, we'll get to some of these other things in just a moment. So this is the track of the North Magnetic Pole. Over the past few hundred years, it is supposed to not be stable. It's supposed to move around just a little bit. Of course, around 150 years ago, it started to hit the gas, kick up speed, and is now racing across the Arctic Ocean. There has been a much more stable pattern of velocity to the motion of the south magnetic pole, although it is definitively increasing about 6 or 7% of its velocity every 20 or 30 years. And as you can see, this is coming up south of Australia. This one is going to be curving down onto Siberia. And so those two things bring you to a meeting point right there at Java, Indonesia. Now, as these things are happening, Earth's magnetic field is weakening. We had our zenith magnetic field about 3,000 years ago. That's when it peaked, but it's not like it peaked and came back down a lot. It sort of rode there and sort of slowly started to come back down. We really started to notice a meaningful weakening in geologic and actually some of the old navigation records from some ship captains. We are noticing that around the time of 1800, 1850, our magnetic field started to really weaken. Same time the poles started to really speed up. And what I mean by really weaken, from about 1850 to the year 2000, it was noted that 10% of Earth's magnetic field had been lost. But that number was upgraded to 15% just in 2010. So that's 150 years to lose 10%, and then just 10 years to lose another 5. Extrapolated out, 20 years to lose the same amount that you lost in just 150 before. And plotted, this is actually what the curve really seems to look like. Around 2025, 2030, 2035, if trends do not change, we'll be down 50, 60, 70% of Earth's magnetic field, and things will start to get really scary. Of course, things could change at any time. There's no reason why these patterns that have been persisting for decades and decades now here couldn't change at any moment. And there is no reason, I don't think, that the millions and millions of years of Earth doing this exact same cycle over and over again, maybe the Earth just won't do it this time. That's not where I'm placing my bets. So in 2015, fast forward 5 more years, Swarm did not give us a new percentage down, but they did say that the trend was continuing and continuing to accelerate, and they indeed confirmed that the weakening of the magnetic field was due to the movement of the poles, which really actually kind of makes sense. And we'll get to that here. So the small star off the coast of Indonesia, that is where the north and south magnetic poles are set to meet. Is this just a random coincidence, or should we assign meaning to this? Well, let's look at the exact opposite side of the globe, and that's the much broader white diamond sitting in northern Brazil, Venezuela, pushing up into the Atlantic there. Those are the opposite sides on the planet. Now, the blue triangles are the Bermuda Triangle and the Dragon's Triangle, and the blue star are the weakest fields on the planet, and the red star are the strongest fields on the planet. So we have the place where the poles are going to meet, pretty much adjacent to the Dragon's Triangle, which is their version of the Bermuda Triangle, and the strongest fields on the planet. The exact opposite side of the world sits between the Bermuda Triangle and the weakest fields on the planet. Now, the weak versus strong fields is actually nothing that, really nothing all that complicated. If you think of the globe and you have one magnetic pole on the north, one magnetic pole on the south, exact opposite sides of the world, pretty evenly distributed. But what we have right now is the South Pole coming up basically where the red star is right now, the North Magnetic Pole coming down through Siberia, both magnetic poles are moving away from Brazil, away from the central Atlantic. And so the magnetic poles of Earth are getting farther away from the South Atlantic anomaly, basically around the blue star, which is why that area is weakening in magnetic fields faster than all the others. It likely does not have anything to do with the core. So Earth's magnetic field, just real quick, good way to think of it, because we've heard a lot about magnetism and even a lot just in the last few minutes about Earth's magnetic field. To reiterate, it is the primary thing standing in the way of the interplanetary magnetic fields having basically free reign over the global electric circuit, which we're going to see in a moment involves the lithosphere. So, once that energy comes in, what happens to it? How does that energy get anywhere near the ground? Well, we're going to start with the global electric circuit, and in this presentation we are using earth.nullschool.net, which many of you recognize from the Null School runs in the morning news. White is high pressure, purple is low pressure here. And now, there's a general rule with the global electric circuit. In fair weather, high pressure, clear skies, the global electric circuit sends currents down to the ground. And it's been recently found that on the sun-facing side, during CME impact and the compression of the magnetic field, that this can actually increase that downward joules current. And then in low-pressure systems, it is sent back up, sometimes very quickly and violently, like in a terrestrial gamma flash, which would be our version of a solar flare. So what we have here, just as an example, if you were to look at this and I was to ask you, where are the global electric circuit currents coming down to the ground from the ionosphere, and where are they coming back up? They are coming down over the western United States, that is the highest high pressure, and they will probably seek to come up both in eastern Canada and off the coast of California there. That's how the global electric circuit works. High pressure brings the currents down, in addition to the air as well. The reason why you see high pressure systems, when you look at them from above on the wind map, why they're all pushing outward, but in that clockwise or counterclockwise fashion in the south, the reason why it's all pushing out is because it's all coming down. It doesn't have anywhere to go. It has to spread out. And in low pressure, the reason why you see all the winds coming and sucking in, where do you think they're going? The water vapor in the wind moves along with these currents. Now, that's something we're going to see a little bit later as well. So, what we're going to do now is watch a video that's going to be an over-exemplification of what is very subtle and faint, but occurs over vast scales on our planet. All right, so these videos all come from Yelverton's lab. If you have gotten a chance to read the second new paper that we've published, a lot of these images are actually in that paper. What he's doing here is he's simply discharging electricity to rock, because we know that those downward currents from the ionosphere, sometimes they'll hit orographic features, sometimes they'll produce clouds, sometimes they'll juice up existing clouds or storms, but sometimes they will make it all the way down to the ground. And if you'll notice, it doesn't really integrate. It sort of seems to find the paths of least resistance, which is something that electricity texted me last week. He said he likes to do that. So you'll see that it's always in the cracks. Where can the electricity get through? Well, you can think of a lot of situations where this might be the case on Earth, but the biggest ones, the biggest cracks, the biggest way down to the ground is the fault lines. Those are actual cracks and areas that generally contain low resistivity crustal contents. That is something that the mainstream just happily dropped on our laps a couple of years ago as they really brought all these studies together. All these fault areas have extremely low resistivity, meaning that they're going to let these currents come through. Now we're going to scoot forward just a little bit here. So it doesn't matter if we start low, if we start blasting full bore, or as you're going to see here, as we start low and build and build and build and build. Now we have all the lights off, so it's not as easy to see, but you see the current doesn't meander around. It's looking for these paths of least resistance that are already there. Sometimes it finds one quite violently. Go forward a little bit more. There are some rocks that simply refuse to cooperate, even when it looks like they might have cracks in them. Now, you were watching granite, sandstone, limestone. Current's going to get through there. This is quartz crystal. Quartz says, you shall not pass. And this, now we're starting to get interesting if these currents can get into the ground and start interacting with rock. This is, by the way, the sandstone, and you can see that the current has absolutely no trouble passing through this very porous rock. I'm going to go ahead a little bit. Quartz will not let it go any way we tried. Believe me, Billy put on his Thor costume and blasted the crap out of that piece of quartz. We cannot. It will not let the path go. This is limestone, I believe, and you can see the current really is. It can find the pathways through there. It doesn't need to go around, and it works very, very well like that. We'll turn the lights off here so you can actually. We'll go back. Turn the lights off here so you can see that you can see it illuminating. It's coming in both sides, but it's illuminating parts all throughout. So the current can flow through some rocks and will, but others will direct it around. And we're going to see a good example. We're going to turn the lights off here. That's the porous limestone on top, the quartz below, and you can see, well, current might come through some rocks and then just decide, oh, I'm going this way, or I'm going this way. So that is one way that these currents can actually begin to access the crust or maybe even further down. All right, so this brings us to our deep earthquake mystery. Now, why is there a deep earthquake mystery? Because the way we think of the crust breaking and shifting and thrusting does not work so well. It is not very convenient to describe action or causation of action deep within the more viscous fluid mantle, does it? Doesn't really seem like it should build up stress and then break. It should be much more fluid. So we have a lot of deep earthquakes, some much, much lower than the crust. And how do we account for them? And much more interestingly, why does it seem like these are the number one subterranean signal for a larger earthquake to come at the crust? Well, there are probably some folks here who aren't in love with plate tectonics. But there is something about plate tectonics which I will absolutely refuse to bend on, and that is subducted plates, or the notion that part of the crust definitely dives down underneath. You know, deep earthquakes are not randomly located. The only areas we will see deep earthquakes are right at that subduction zone, and if they are shallower deep quakes, they'll be closer to the fault. And if they're really deep, they'll be on the direction where that plate is going down. That's how we really know that they're there. These plates that are subducted, this is where all the deep earthquakes take place. And if you're talking not about viscous, fluid mantle, you're talking about cold slabs of rock. Yeah, I'm sure the top and the bottom of them touching the mantle are probably not cool. But we're talking about kilometers of material. There's still liquid water in there. There's liquid water in this thing that is being plunged into the mantle. This is where all deep earthquakes occur. We do not see deep earthquakes happening anywhere else. And if you were to plot them on something that looked like this, you'd see deep earthquakes going down on that diagonal. We don't find them anywhere else. So what exactly are we seeing? Well, we have three important electrical effects that could be accessing the mantle and could be causing some of these deep earthquakes. Now, you remember I mentioned this earlier about the compression of a CME impact on the sun. That would be what the yellow wave is. It compresses the magnetic field, compresses the Van Allen belts, can even push them into the atmosphere. And that can indeed add to the downward force under high pressure, the downward currents to the ground from the ionosphere under high pressure under fair skies. So that's one way that we have an increase due to space weather in terms of the energy that can access the ground. This is from the European Space Agency, We, of course, do have induced and coupled currents, and those include currents inside the mantle. So we know that we've got currents down there. In addition to them finding a way down to access, we know that they're just simply induced there. And then, of course, we have something that you may recognize somewhat from Dr. Claridge's presentation. We have the in-out at the poles, which is really not so much guided by the straight-on force of the solar wind. This is more what's guided into the cusps, what the plasma tubes and the L-shell magnetic fields of Earth really sort of funnel towards the polar regions. And, of course, those will play a role in the secondary, the plasma tubes, the ionospheric currents, and those are going to have more induction effects as well and also play in the weather. So, coming back to this idea that we have currents that could access the crust via fault lines, and I asked myself, do we actually need them to be induced by geomagnetism? Do we actually need them to seek a low resistivity crustal content in a fault line? Or can we just have a much, much easier route for these currents to get down into the mantle and into these subducted crusts? Well, this sort of circular, half-circle looping arrow would be the induced magnetic current. Of course, we have to imagine what comes down through the global electric circuit and finds a fault line. But what is that sideward L-shaped arrow? Does anybody know what you call currents that travel through the crust like this? We call those telluric currents. And they are very, very real. And what happens if you've got a subducted plate and you've got telluric currents running through that plate? The currents are going right down with the plate into the mantle. And so we have a lot of these different ways for this current, this energy, to access these deep areas where we see earthquakes. So then the question becomes, is it possible that they have something to do with the nucleation of those earthquakes? So, just to quickly go over what we talked about there, we have the space weather-induced currents, and a lot of that does include the telluric currents. We have the global electric circuit flow down and up, high pressure, low pressure. But what about internal sources? Something that didn't come from the sun, something that wasn't part of Earth's global electric circuit. We've got even more sources of electricity here. Because you see, we've got charge transmission and domain rearrangement. As this cold slab of cold rock and water is pushed down into the mantle and it is heated and it is crushed, we have rock and crystal deformation. It's mainstream science that those give off electric currents. Of course, we have the thermoelectric effects as well when you are heating up that material that was up there at the crust and now you've plunged it into the mantle. You've got thermoelectric effects as well. And so we're really talking about piezoelectricity, pyroelectricity, and you don't need anything but just to push that cold earth and the water down into the mantle. And of course, we have the electrokinetics of the water flowing through the porous rock like the sandstone that we saw. And so we have many sources of current. You know, whether it's the sun, whether it's something with the global electric circuit, whether it's induced, whether it's telluric current. So what are the effects of some of these things? Well, we're going to look at some more stuff from Billy's lab right now. We're going to be investigating the effects of electric current on water and the number one upper mantle mineral content, and that is olivine and its water-rich polymorphs. So this is going to be the effects of water, or the effects of electric current on water and olivine. Now, these are done in the lab, and here's what you'll have to remember. Water is more volatile and olivine more conductive at mantle conditions than it is here in the lab. So anything that we see here will be equaled or amplified under the mantle conditions with that pressure, the temperature, etc. So this stuff is really cool. He started without any arc. That is a drop of water. This is not sound vibration. This is not cymatics. This is just electric current in dark mode. Before we saw it in lightning mode, discharge, arc mode, where you could see it, that whitish, purplish plasma. Here, He just didn't turn up the power enough to do it, because if you actually do get an arc discharge, all the vibration and cymatic patterns disappear. So we're going to zoom in a little bit on it here. When he turns on the current, all that is an electrode above. Technically, that would be the anode. The cathode would be below. But you should be able to see how the water is sort of rippling around and moving. It happened too quick there for you to see, but when there was a little lightning bolt, everything went calm for a moment. But there's more than just the shaking, because when we get to real power, and this is just water with some pyronine added for visual effect, water will be attracted to this current. Water will get pulled by the current. So you could see there, the current was just going into the crack, the low resistivity zone, like it's supposed to. But the water knew this was going on, and the water wanted to come be a part of it. Now watch this. This is how attractive current is to water. It is painting the fault lines of the rock with the pyronine. Now think about this at the scale of the Pacific Ocean, at the scale of enormous plates. But if you're going to be thinking about it at that scale, we might want to think about, well, okay, it cannot just be attracted, but look at how it's pushed out among the lightning bolts. Now, granted, we don't have literal lightning underground, although some folks at the USGS are actually starting to think we do. This is really cool. Watch what happens. So much for gravity. When we hit the current, that water starts pushing up on the sandstone. Now you start to think of this over the scale of a country, over thousands of miles. These tiny subtle effects of water pushing up or pushing down or side to side. This is olivine crystals right here, and they can shimmy a little bit on charging, but when Billy goes to discharge them, that's when we really see the action. They self-translocate relative to one another as they are discharging their electricity. We'll just watch a little bit more of this here because it is super cool. And so as you can see, he'll nudge some and they'll jostle, but what that is that's a grounding rod. He's grounding them. He is discharging all of the electricity that he fired in. Now, what I didn't show was he spent about 60 seconds to 2 minutes firing 70,000 volts into these crystals. So these things aren't just, you can't just grab a bunch of olivine and go do this on your table. We charge them up, just like they would if they were introduced to electric current down in the mantle, and extra pressure and extra temperature, things of that nature. This is really cool. So no current right now, and as we turn the current on, the olivine acts like a magnetic field and starts spinning the water around it. Do you see the particles in the water spinning? That's just the current hitting the olivine. So we have water in these subducted crusts. The number one mineral component of the mantle is olivine. And look at how they react to electricity. It's preposterous. Okay, so we have our water and olivine effects from the current. They appear to have the ability to translocate just based on their interaction with electric current. And of course, if you get the electric current down there, you will also have heat created when it interacts with the resistors. You'll have the magnetic fields created by those currents. And then, of course, you'll have electrolysis if it hits the water, splitting into hydrogen gas and oxygen gas, which is extraordinarily volatile. But we also have the electromagnetokinetic phenomenon. And I'll be darned if this isn't utterly absent from modern academia. 1953, Alexander Colin studies and reports the electromagnetokinetic phenomenon. Almost nobody in academia cites it ever, but it is used almost ubiquitously in the separation of melted metals, in biological applications like separating biological materials, DNA, and other things like that. When it is used in smelting and separating melted aluminum and things like that, it's called electromagnetophoresis. Or when they're talking about separating biological materials, they refer to it as electromagnetic buoyancy. But it is all the result of the electromagnetokinetic principle from 1953, and that is that even if the matter is neutral, it can be translocated by enough current. And the push is perpendicular to both the current and the magnetic field. And so that's what this looks like. If you've got current coming one way and the magnetic field wrapped around it, those pushes outward from the magnetic field, which are perpendicular to the magnetic field, but to do that they have to be pointing out in every direction around it. And in doing so, they're also perpendicular to the current. This is why whenever Billy puts an arc discharge into the ground, it blows out a perfectly circular crater, because it's going in, the magnetic field's going around it, and there's an equal push all around. And we've had a number of you guys in some of your own home laboratories recreate Billy's arc discharge craters, and you really cannot tell the difference between one of those and an alleged boloid impactor. So, what is our deep earthquake mystery, really? We've got these plates. Maybe they're not plates fully in the way plate tectonics wants us to believe. Maybe they are. But one thing's for sure, we only see the deep earthquakes where one goes under another. And inside that area that has been sentenced to go, however knows how long, inside the mantle. That's the only place we see these deep earthquakes. They go down in there cold, and they're constantly changing, and they're deforming, and they've got water in there. They happen to go down at the area where any global electric circuits coming down are going to find that low resistivity crustal content. They're the areas where the telluric currents are just going to ride that crust directly down in there. We don't need to be induced by space weather. We don't need to have the global electric circuit find a fault, although they are valid ways of getting this done. All you'd actually need is the telluric currents to ride this crust down into the mantle and start affecting olivine and water and some of the other rocks down there as well. So, what we have here, just to sort of quickly summarize that portion, is we have a space weather and geomagnetic and global electric circuit effect, potentially, on the production of piezo and pyroelectricity. Because if it's getting down there into those subducted crustal areas, it's going to create heat, magnetic fields, it could move the water around, and we're talking about rock deformation, charge transmission, a lot of exoelectron stuff there. Of course, the thermoelectricity as well. But we can also see these have an enhancement of the electromagnetokinetic and the magnetohydrodynamic translocations of geologic material due to that current. All of the different examples of how this could be done, you know, whether we're talking about the sun inducing, whether we're talking about the global electric circuit, whether we're talking about just putting that cold slab of rock into the mantle and letting pressure and temperature create the currents. Only one of these mechanisms is required to potentially create these deep earthquakes, and all of them are possible. So that brings us to Blot echoes. That is what we have termed these deep earthquakes. Blot echoes, the name is a combination of Claude Blot and the username Hook Echo, who we now all know to be Scott Windbeal. He is one of the more prolific commenters on YouTube. He's been a big part of the community for a while. And so Claude Blot is the man from France who first noticed that by tracking these deep earthquakes, you might be able to tell where subsequent ones would occur, although he mainly was focusing on volcanic eruptions. And so that's where the Blot comes from, and the person who introduced us to his work and has been standing there right next to us, pushing it forward in every step that we have, if not more, is the guy who goes by the name Hook Echo. So a Blot echo would be these deep earthquakes that are indeed echoing the introduction of electric current into that material. And generally they have to be larger than magnitude 4, and they have to be at the low velocity zone or deeper, which is normally about 100 kilometers or down, can be as shallow as about 70. So now let's dig into a little bit more about how we actually pinpoint the areas on the world that are going to have these earthquakes. And so you'll remember we talked a little bit about blot echoes and exactly what those are and why they're called blot echoes. Just a quick reminder, those are deep nucleation earthquakes, low velocity zone or lower, generally starting at about 100 kilometers. There are a few places in the world where the low velocity zone starts a little bit shallower, around 70 kilometers. But in general, we're looking for magnitude 4 and higher, deeper than 100 kilometers. The other primary factor we're looking for is what we call earth spots, and that would be the interaction of the high and the low pressure systems on the planet. Since this whole thing is about the potential for electric currents to be affecting the water, the olivine, deep in the ground, well, we look at where that energy is coming in and where it's going out. Sometimes it's as simple as just looking at where the low pressure system is. Where is it going to be trying to pull that energy out? And sometimes you have to get a little bit more creative and look at the high pressure to see where it's coming in. This is pretty much where we've left off here. This is the spring of seismic forecasting for a number of reasons, not the least of which being temporal and it being the spring. But so now it's time to actually look at the model in action. And so we're going to go through a couple of examples. Let's start with an area you might remember. So far, South America has not let go a magnitude 6 event that was not in the highest alert zone. Remember the highest alert rule. We could have 100 little red lines on the map, but if there's one alert star, that is the only highest alert. So remember that. So at no point has South America let go without that specific region being on high alert. And you might remember that there were 2 consecutive events where we basically put that giant alert star in the same place. And it was because the signals that were presenting at that time were exactly the same as one that happened not too far into history, actually, but just back in 2015 when a magnitude 8.3 struck Chile on September 16th. Now, this is very much the same situation that took place this past November, twice, when we got those 2 6-pointers there. And so this is what the wind map looked like at that point. Very easy to pick out the low pressure cells in southern South America, but what might be a little bit more difficult to pick out, where Chile goes north and then bends to the west at Peru. Right where the Andes Mountains are, you should be able to see a little bit of white on top of those mountains. And of course they're surrounded by yellow, indicating a higher pressure situation. Now, I'm not sure how much you guys know about South America and the pressure situation, but basically, east of the Andes Mountains, especially in Brazil, it's almost always low pressure. It's almost always below average. And so this was much more high pressure than you'd expect. And if you can't see it here, you can go pull up earth.nullschool.net, and they have a time feature. You can go back in time and look at this. But so essentially, we could tell that on the landmass, the current was coming in somewhere around Peru, right around the Andes Mountains. And we might expect it to come back out at the low pressure system to the south. That's just looking at some of the current. We know it's going to come down, and we know the low pressure is going to bring it back up. Well, while this was happening, all right, and the blue arrow on top is supposed to be your global electric circuit current coming down. I don't know the best way to draw that. That's just supposed to be the down and the coil around it. But those numbers right there, those are the positions of blot echoes that occurred within about 48 hours of the 8.3, which occurred at the red star. And the 1, the 2, the 3, the 4, simple enough, is the order in which they occurred. So the pressure was coming down. The currents were coming down on Peru. If they were able to get into this fault system here and get underneath the ground, whether it's by induction, direct GEC push, or by telluric currents just riding itself down there. 1, 2, 3, 4, migrating from the position of the downward current towards the position of the eventual magnitude 8.3 rupture. Any of that sound too complicated? It's not. It's very simple. There's no guarantee that that downward current's going to make it to the mantle. It's going to make it to the subducted crust. For all we know, it could hit orographic features and produce clouds. It could just ionize the air and make it easier to produce the clouds. But we do know that cosmic rays are a player at ground level, and the global electric circuit can absolutely reach the ground. And so if it was going to get in there, in between those two slabs, and travel down to the south, and be moving water, be moving olivine, be affecting piezoelectricity and pyroelectricity and exoelectron emission, charge transfer, domain rearrangement, you would expect to see it breaking and breaking and breaking along the point to where it was going to eventually try to come out. So let's take a look at some Blot echo situations. So these are, the little circles you see right there are all Blot echoes of sufficient magnitude and sufficient depth, and they all struck between November 9th and the morning of November 13th, 2016. Do we remember what the larger circle with the X through it is? That was their 7.8 that struck later in the day on the 13th. That is way too many Blot echoes for northeastern Oceania. When you see a cluster like that, it usually means something big is coming. And if anyone remembers, the interesting thing about the big earthquake in New Zealand was it hit during a storm. The low pressure system was right overhead. It's actually more common in the Philippines than in New Zealand in terms of being directly overhead. But we had a ton of Blot echoes, way more than normal. We usually get 3 or 4 over a given week in this area, but this was in just 3 days, and that's more than 3 or 4. So let's stick with New Zealand for a little while. You might remember they also had a 7.8 back in 2009. This was a nice little swarm of Blot echoes. That was just the 12th, the 13th, the 14th, and the 15th. So over 4 days, we were well over average for an entire week. And this is also in order over on the left side there. It's in descending order, starting with the most recent one. So the most recent one was the one that was closest to the eventual rupture. We call this Blot echo migration or transmigration. Which direction is it going? Because it's not always directly over top. You saw in the South America example, the Blot echoes track towards the eventual zone. Here, the Blot echoes track towards the eventual rupture point. Let's keep going, shall we? 6.1 and tsunami, February 21st. Now, granted, this wasn't as large of a magnitude event, but this will go down as one of the more well-known because of what it did to Christchurch. If anybody remembers how bad the tsunami was back there in 2011. Well, we had a major flurry of Blot echo activity that actually included a Blot echo that was larger than the eventual crustal rupture at 6.5. So again, you see a ton of Blot echoes here, much more than the 2 or 3 that would be expected in the week before that in this area. We got one more here, and this one, this was a nice crack on the Kermadec Trench at 7.4. And I've actually left the 7.4 on there so you could see it. You can sometimes see these swarms, and it's difficult to know where this crack is going. Sometimes a Blot echo and swarms of Blot echoes in northeast Oceania, they will actually migrate west across the Solomon Islands, across to Papua New Guinea. Of course, it's usually the weather that tells us it's going to do that. All right, so let's come back here. This is, of course, the small little circles you see in northern Chile, in Bolivia, in Argentina, and then actually up in Ecuador as well. All occurred between February 24th and February 26th of 2010. Does anyone remember what happened one day later on the 27th of 2010? An 8.8 struck Chile, and that is the big line right there. This one is interesting because I actually don't believe the Ecuador Blot echo really was even involved. That may have even just been too far off and just sort of a random anomaly. We do see the cluster of Blot echoes much further south, actually bordering, kind of where Bolivia, Argentina, and Chile meet. So of course we've got more little we've got more little circles here and another big one with an X, and let's see if we can figure out what the big one with an X is, because those Blot echoes were March 7th, March 8th, and March 10th, 2011. I assume we all know what the big X is, right? The Fukushima catastrophe. I've left the 7.9 on this one as well. It looks like Blot echoes are much less common when you get to the higher latitudes. They are much more common as you get towards the tropics, and so seeing two basically straddling the position of an eventual 7.9 that struck Alaska in 2014, two up there is something you start to pay attention to as well. This is actually the wind map from that day. You can see the storm that's coming off of Japan. That's a fairly common thing when they form. The moment they get off into the water, they are gone. You see the Aleutian low there as well. For those who don't know why it looks like there's always a low pressure system up in that bend of Alaska, that's called the Aleutian low. It is a semi-permanent thing like the Siberian high pressure system. There's an Icelandic low that sits over Iceland, and an Azores high that sits over the Azores Islands of Spain, or of Portugal. I'm not sure exactly. Is that Spain or Portugal? Portugal, sorry. But here we have this low pressure system right there due south of the eventual rupture point, and it almost appears like it's the top of the pyramid there is its own little low pressure system, kind of ignoring the fact that the pressure cell is supposed to be to the south of it. Almost like there was a pre-seismic signal there. But so, granted, we've got the low pressure system, which doesn't look like a normal low pressure system. It's sort of got that extra node up there where the earthquake occurred, and of course we had the two Blot echoes straddling it. And when you've got both the atmospheric and the subterranean signals sort of looking, when they're both pointing at the same area, who says they might not interact there? Let's keep going a little bit. So we'll remember that the 6.6 that struck Italy on October 30th, remember we talked about this, it was the 14th or 16th largest event in the entire history, recorded history of Italy. And you might remember there was an alert star over Italy the day that happened. It was, in fact, the first and only time an alert star has ever fallen outside the Ring of Fire. We've never seen cause to put one outside the Ring of Fire other than this. So let's go see why indeed we put an alert star over Italy. So on top you have two wind maps, two images from the wind map, same general area, Mediterranean Sea and Italy. Down below you see the two Blot echoes that preceded the magnitude 6.6 in Italy. And interestingly, both of them came after. You might remember there was a 6.1 that struck Italy on October 26th. And normally, 99 times out of 100, that's the rupture. That's the end of the seismic event. That is the primary main shock when you're talking about Italy. However, immediately following that event, we have a 5.8 Blot echo, 450 kilometers down. And it corresponds with the image on the left. Note the central node of the low pressure system. If you draw it directly north, it basically looks like it's hitting where the island comes and meets the mainland there, sort of the end of the peninsula. Then, one day later on the 29th, there is a slightly smaller but more shallow. It's coming up to the crust at only 270 kilometers, another Blot echo. And look at where the low pressure system is moved. So what we have is we have Blot echoes approaching that fault line, not only in geolocation looking down, but in depth as well. It's approaching the crust. And we have a low pressure system ready to get right over top of that fault line. Well, over the next 12 hours or so, that storm did move over the fault line, and when it was directly over the fault line is when the 6.6 struck. And granted, it was a few hundred miles away, but kind of tough to ignore something like that. It was a few hundred miles away from the actual low pressure system, which is something we see all the time in Mexico. I think I'll bring up actually. I mentioned that Philippines, they do tend to rock when the storm is overhead. Japan likes to rock where the storm is going. And Mexico likes to rock due north of a system that is just tracking in the Pacific. You know, the fault area just north of that tends to crack more than any other area, basically from Central America up to Los Angeles during those periods. Speaking of California, there has been only one magnitude 6 earthquake in the United States since the model began running. Granted, it's still in its infancy, but we did get one. Magnitude 6.6, December 8th. I believe I did show you guys the alert map for that. But if not, it was under a red alert. You can go and find that on Twitter. By the way, all these maps are public and posted, and an entire spreadsheet list of all these things can be found on QuakeWatch.net. with links to the Twitter timestamp posts, because without a third party, how are you supposed to trust anything? So these two pictures are the atmospheric and the subterranean setup that cause us to put the region on alert. And so on the left side, you see we've got massive high pressure, and also we had a CME impact, a coronal hole stream impact, while the sun was pretty much right over the eastern part of the United States. Due to solar tide, the east-west signal pathways, it was the high pressure over the western United States that really took the compression energy and got that extra push. Now that was on December 7th and the beginning of December 8th. And if not for the foreshocks, I'm not sure I would have seen reason, just based on the space weather, to see this high and low pressure system as being so interconnected and being able to actually release something through the fault. There are no Blot echoes in the United States. Never seen one. They don't happen. But it's a simple matter of seeing slightly higher earthquakes than you think California is supposed to be getting in a cluster. And if you see them migrating, like we've seen Blot echoes migrating, then you've got something. So look over on the right side. A 3.9 struck inland California on December 4th. At exactly on the coastline, a 4.3 struck December 5th. And then a 4.3 struck out in the ocean just north of the Mendocino Junction on December 6th. So we've got increasing above average magnitude for California. And so we have this increasing magnitude trend in the direction of this low pressure system, which is kind of oblong and kind of oddly shaped anyway, sort of reaching down towards that fault system. You've got the low pressure earth spot over top of an area where pre-seismic signals in the ground is moving. It's just the same thing over and over and over again. Now, yeah, there are some tweaks. So in the Philippines, I worry when the low is overhead. In Mexico, I worry when the low is 200-300 miles, 500 miles offshore to the south. Sure, there's no Blot echoes in the United States, but these are all above average earthquakes, and they are trending directly at the eventual rupture point, where you'd expect it to be based on the pressure systems. There are slight tweaks, but in general, it's all the same thing all around the world. This is something I like putting. Does anybody happen to know what these images are? I'll give you a clue. It's the Philippines underneath there. The clouds are Typhoon Yunya, and the darker gray is Mount Pinatubo's 1991 cataclysmic eruption while the storm was directly overhead. And interestingly, there were Blot echoes that preceded the volcanic eruption, although one could argue that they were preceding some of the 6 magnitude earthquakes that happened when the storm was there anyway. Just really interesting little thing there. So coming back and reminding everyone that during those first 100 days, because I honestly have to attribute it to luck in getting a streak of 9 of these big quakes in a row, we were higher than the expected average at 83.3%. Based on the actual statistics and how these things have played out in history, whether you go with 5, 10 to 20-year histories, this model should get between 70 and 80%. So this was a little bit better. But something that I've been trying to work on is decreasing the size of the alert zones. And so what we have here is where we are currently. And so currently we're much closer to reality as opposed to being up in the stratosphere at 75.7% of the big earthquakes using 16.6% of the actual fault zones. Let's take a look at a pretty good example of something that happened since those first 100 days were up. As I mentioned before, 9 Risi created the Blot Echo wind map. And that's so that you can look at the Blot Echoes while you're looking at the pressure systems. Those two factors now in one place on one map. And we're actually going to go over to QuakeWatch and see that in just a moment. But for this, I wiped the wind layer off. I just wanted to see the Blot Echoes. So I could show you guys that Blot Echoes happen all over the place, but are you getting more than one? It's where are you getting them? Are you getting them in succession? And of course, we had a 6.3 to strike Papua New Guinea right in the middle of the largest red circle there. This was an alert map that we posted on February 20th, and I've zoomed in on the right side on some of the on just South America. This was another one of the examples. If you can go back and picture what some of those alert zones were looking like before. Maybe this one in the middle over there on the right would be connected to the one on the north or the south. And so we're starting to be able to break these alert zones that used to exist as longer continuous lines and really make them smaller. And you can really see that here on this map where normally we would have 1 or 2 long line alerts. Now we're able to really pick out much more specifically some of the areas. And of course, it was just one day later on February 21st that the 6.5 struck in Bolivia. I'm not sure if you can see over on the right, but it was literally dead right on that red line. All right, so what comes next? For me, it's continuing to do these forecasts. It's continuing to refine the model. It's continuing to work with 9 Risi to actually get this to be something that is much more objective than subjective, because there is very much a subjective element to it right now. There's probably a way to graphically tell exact vectors of migration. I'm eyeballing it. There is probably either the European model or NASA's GFS model that is better for predicting pressure systems. Right now, I'm using them both, seeing what they both predict, and guessing which one's going to be right. There's a lot of improvement that can be done here. But in addition to there being a lot of improvement, there's a ton of room for you guys to get involved with this. The search tools for earthquakes are so robust that just about anyone in a few minutes' time can go onto the USGS site and learn how to quickly use their earthquake search tools. And so how hard would it be for you to pick out maybe a place where your family was from long ago? Maybe your family comes from Italy. Or maybe you've got a son or daughter who's studying abroad in Japan. Pick a spot in the world. Figure out when the big earthquakes were. And then, normally the hard part is you have to go find the pattern. I've already told you what the pattern is, what you need to look for. What I didn't do in these papers was do a historical proof. I let the numbers and the results speak for me. But normally in academia, I would have had to have shown why Blot Echoes worked in every little place around the world. It would have basically been 10 to 20 page papers for every segment in every region of the world. But by circumventing that, we have created the opportunity for these subsequent smaller scale analyses that just about anyone could do. And if anybody does want to undertake that effort, I'm going to be sort of getting a list together, and regardless of how easy some of the pieces will be, I will go through and show you how to get the earthquakes you want for the specific times. I will show you how to even pick out depths and magnitude. I will help you with some of the thought processes, and I will help edit any papers that come in on this, and I will help promote them. I'd like to say I'd try to help them get published, but I think we're going to be doing most of our own publishing for quite a while. But this is what I'm talking about. What I showed you here is not that difficult, presuming you can go find the data. You start seeing deep earthquakes occur. You start watching the pressure systems. I mean, you can predict earthquakes. There's no reason you can't. And I will help you get recognition for this. And that is probably what this is going to take, because the skills that the world has presented in being able to ignore this are some of the most impressive I have ever seen. And so I was talking with Bruce Laborn a little bit about this before I came up here and got started, and I'd like to share a little something about this. What we're really trying to do is we have to circumvent academia, because otherwise I've got to get somebody to listen to me, and then I've got to get a few scientists to agree that a paper is worth publishing, even though it's going to go against a lot of the things that got them to where they are. I've got to get them to convince the larger field and then the global consortium of scientists, and then have that influence policy in people's minds. You don't have to do any of that if 1,000 people are out there predicting earthquakes. If 1 million people are out there predicting earthquakes using things that are free and open source and easy to understand, then you have circumvented that system, and you've just basically brought that truth and that gift to the world just right out of the ground as a polished ring. You really have. And that is the power of open source. It really is. Just as my eyeballing it is going to look very amateurish when we get some programs automating these things, the power of your imaginations and your creativity and your ability to see other things that I will not have told the computer, that we will not have put in the programming. That is how this actually comes together. But I can't do it by myself. You guys have to do this with me. There is one thing I have not shown you guys yet, and that is outgoing long-wave radiation. Because this is, sometimes there's low-pressure systems all over the place. Sometimes it's really difficult to actually tell. You know what, I'm just going to have to actually find the bookmark for this, because I don't know how to get there otherwise. You can laugh at me anytime now. Well, there we go. All right. So, this is the latest, the last day's outgoing long-wave radiation anomaly map. Not the actual outgoing long-wave radiation readings, just the anomalies. Now, what we're looking for to confirm that atmospheric signals are what we think they are in terms of pre-seismic signals is within the tropics, at least 120 delta within 12 degrees, and that number I believe drops to 90 as we get into the higher latitudes, like say if you're talking about Japan or you're talking about southern Chile. And so it's actually not that hard to eyeball this. We are going to put it into a program, but each one of these hash marks, 10 degrees. So very, very close to your 12 right there. The scale down there at the bottom with the colors, easy to see what the values are as well. If there's any meteorologists out there, they're probably shaking their heads saying, dude, what are you doing? This OLR map is not what this is used for. But it is only about 90 to 95% based on wind and clouds and precipitation. Sometimes you see these anomalies on there, and the weather doesn't seem to suggest that they should be there. A lot of times in those cases, it's where an earthquake has just occurred or there's a volcanic eruption taking place. So you've got to factor that in as well. But if it doesn't look like the weather should be causing these anomalies, and it's very simple. Sunny skies, high pressure, a lot of energy coming in. It's a lot more energy to go out. That would be the positive, the brown, the yellow, the black. The deficit of outgoing long-wave radiation is when you've got clouds there and you don't have as much release because, well, first of all, you don't have as much coming and hitting the ground. And a lot of what does hit the ground can be trapped by the clouds. And so when you get these strong storms, that's when you get the negative anomalies, high pressure, sun, heat, positive anomalies. Another reason why the anomalies are strongest at the tropics. That's where the majority of the heat is. That's where the strongest storms are. And so this is used in conjunction with those atmospheric signals to actually put areas on alert. Now granted, I imagine most of you have this tiny little light bulb that's starting to flicker on, but you probably don't feel like it's on just yet. Welcome to how I've been feeling since October of 2016. You literally just have to trust that it's this easy. And this is what QuakeWatch.net is here for, so that you can see these things and you can practice, because there's no other way. I didn't just get up and start. Well, actually, that's really not true. The first 2 forecasts I made got 4 earthquakes in them. But all right, so you don't just get up and do this. I did fail the next 3 times. But you don't just get up and rock this thing. And it's going to take a long time, and I can honestly say that I will be able to do and deliver these numbers over long periods of time, probably as long as seismicity exists as it does today. If I was to use these exact signals starting in 1980, I would have 70 to 80% of the last 35, 37 years earthquakes. That's how I know I should be getting 70 to 80% now. But I'm not going to do any better than that just on my own. Me eyeballing things and the subjectivity of the model is, what's the word I'm looking for? It is unacceptable. It is working right now, and it's fascinating, and you guys can all see that it's working. But that's not acceptable. Exactly. We need to get the computers involved, but more, just as much, we need your imaginations and your creativity involved, because academia has done nothing but shove their foot down my throat. And they do not want anything to do with this. Mainstream journals were telling me everything from, I would either get no response, or they would say, well, you're posting your forecasts on Twitter. Is this a joke? Meanwhile, the official statement from the U.S. government about what it should take to be, part of the things in a valid forecast, in addition to the timeline, the location, the magnitude, it needs to be likely to be seen, and in a way that's going to be preserved and proven in time. So Twitter's timestamps are unhackable, and we've got 18,000 Twitter followers. It's likely to be seen, isn't it? But yet this is a joke, and it doesn't count. I've got about 5 minutes here, and I'd like to tell you a little story that has fortified for me the need to circumvent academia with this project. We all have to. Because if there's thousands of us predicting earthquakes, it can't be ignored. And somebody will have to pick it up and run with it. And I can tell you what, eventually, somebody other than us should be picking this up and running with it. This shouldn't be left to me. This should be left to geophysicists working with solar terrestrial physicists and other things like that, although granted they have a nice tendency to bungle things, don't they? We'll pop this off for just a moment. So, has anybody gotten a chance to read my open letter to the USGS's Michael Blanpede? Boy, what a crapshoot, huh? So for a long time, many of you know that we have been in battle with the USGS's Jeffrey Love. But it turns out he had a hand up his skirt. And so here's the basic progression in the timeline. So I make the request in video form of Jeffrey Love. You guys might remember I was saying, hey, I think we've found something. Give me 1 day. You're one of the world's best geophysicists. I actually think I put that. I said Jeffrey Love is one of the world's top geophysicists. I did do that, didn't I? Thanks, Ricky. And I basically was pleading for help. Just listen to me. Hear me out. Well, it turns out that some of our viewers probably sent Jeffrey Love some very, very angry and strongly worded emails, because he sent an email to Dr. Blanpede, who is, believe it or not, a little higher up on the scale at USGS than Dr. Love even. And Dr. Blanpede was, well, I didn't know it at the time, but he was telling him that, yes, it is always frustrating when you are the target of non-mainstream research. And he was telling him how to deal with people, how to respond to these emails. And not a single word about the actual science or the request for help or anything, just here's how you deflect, here's how you quickly acknowledge, thank them, and then push them away. And right along with that, he decided that he was going to write about the most disrespectful things you could write about a journal, about new concepts in global tectonics, basically calling it a silly compendium of vanity papers, basically calling it a joke. Now, surely he thought that nobody else would ever see this email. And we'll get to why I saw it in just a moment. But that was back in late July 2016. Middle of August 2016, somebody sends me an email that says the USGS is having an open meeting about earthquake forecasting. So I call, I get on the list, and I get this email from Dr. Michael Blanpede, who at this point I haven't seen the email. I don't know who he is, but he said, I saw your name on the list. Here's the go-to meeting information, or maybe it was a WebEx. See you there. Here's some documents. Here's the proposed schedule, etc. Never made any sort of hint that he knew who I was, even though he had been emailing Jeffrey Love about me just 3 weeks earlier. Not just me, but all of you, and new concepts in global tectonics. And so maybe it wasn't even appropriate at that time, but he certainly gave no indication that he knew who we were. So you fast forward until March of 2017, a few months later, and we've started QuakeWatch.net, and we are looking for earthquake forecasters. And we have an earthquake forecasting challenge, which you guys might know. The current pot is up to $300 for the first person who gets a magnitude 7.5 or larger earthquake. There are some other rules to that. But in seeing that, I get another email from Dr. Michael Blanpede. Again, no mention that he knows who I am or anything like that, and no mention of our previous interaction in August in the summertime, although who's to say he even should remember, something like me requesting to be on a public meeting, and, I didn't say anything. I just sort of sat there quietly. So maybe he wouldn't remember me from there. But so he and I actually emailed back and forth about 15 times over the following days, and I had explained to him what we were trying to do. He had actually come with some fairly constructive points. It wasn't all just a slap in the face. Some of it was pretty nice. And then I had explained to him my previous interaction with Dr. Love and how frustrating it was, and how all I could really ask for him was that he take our published paper seriously. I informed him that even though I had gotten published and I was attempting to publish again in New Concepts in Global Tectonics, that my interaction with Jeffrey Love got 48 hours into him telling me why the sun couldn't predict earthquakes before telling me he didn't read our paper. And if you're looking at sunspots, solar flares, geomagnetism, or solar wind speed, no, it doesn't. None of those things actually work because they all have to deal with Earth's magnetic field. The interplanetary magnetic fields from coronal holes get to bypass Earth's magnetosphere. That's another topic for another day. So I explain this thing with Jeffrey Love, and he's sort of like, "Oh, I'm so sorry to hear this." Sort of like he's never heard of it before. He has no idea what I'm talking about, and then encourages me to go publish in New Concepts in Global Tectonics, and he assures me that he will read it and he will give it a fair play. 3 days later, the results of my Freedom of Information Act request come in, and they were to see. I required things from the USGS, originating within the USGS or one of their emails that either included my name, Space Weather News, or suspicious observers. And the majority of the 200 or so pages was my 48-hour email barrage with Dr. Jeffrey Love, and they made it 250 pages because they didn't take out all of the previous things. So the very last email had all the previous emails in it. It was like 50 pages long. But the very first thing in the Freedom of Information Act disclosure was the email from Dr. Blanpede to Dr. Love telling him how to deal with you, how to deflect you, disrespecting me, disrespecting Dong Choi, and disrespecting New Concepts in Global Tectonics. Now, you might say, okay, well, he's just a disrespectful wanker, and that's something. But he interacted with me twice under false pretenses and pretended not to know who I was, when Even, maybe, okay, you got a bad memory, whatever. When I brought up my previous interaction with Jeffrey Love, that really should have rang some bells, and you should stop pretending like you don't know who I am. And if you think that way about new concepts in global tectonics, and you know all I want is for you to take this thing seriously, why would you tell me to go publish in a place that you think is a silly joke? These guys are playing this twisted game. And unfortunately, we have been volleying at Jeffrey Love for months. And really, he was doing precisely what Dr. Blanpede told him to do. And some of his responses just didn't make sense to me. Like, I was thinking, Jeff, are you reading my emails to you? Like, are you actually reading some of these points? How are you responding in this way? But it's exactly the way Dr. Blanpede told him to respond. I can't wait to put this on YouTube. But as I said to Dr. Blanpede in the open letter, and I will say, and I'll say it again here now, they better have their eyes on the horizon, because that's a tsunami coming. Thanks for coming to Observing the Frontier, everyone.